We found out that for monatomic gases, all of them, the specific heat at constant volume is exactly 3/2 equal to the value of the ideal gas constant, which to 4 sig figs is 12.47. And remember those units, joules per mole degree Kelvin. So this is a molar heat capacity or a molar specific heat. All monatomic gases experimentally shown have that value for specific heat. The question really is why exactly? And it has to do with how the energy, what happens to the energy. And basically, as we see, the heat energy will increase the translational kinetic energy of the molecules. Go back in my notes here. Good enough. What about diatomic and polyatomic molecules? An experiment shows that the C sub V is greater than 3/2 are. Significantly greater, around 20 or so joules per mole degree Kelvin. Why? And really, to cut to the chase, your answer is there are other ways that diatomic and polyatomic can absorb energy. So if C sub V is higher for these larger molecules, the diatomic and polyatomic molecules, I mean, it takes more energy, more heat transfer, more Q to raise the temperature than for the monatomic. So some of that energy is being absorbed and is not going into the translational kinetic energy, right? Because temperature is proportional only to the translational kinetic energy of your system, or per molecule, the temperature is its translational kinetic energy. And in the end, these pathways, you could call them, these modes of absorbing energy, are also known as degrees of freedom. And without further ado, for molecules that are more complex, that have more atoms than a single atom, your noble gases are all monatomic gases. You have rotation, because the rotation of a point particle doesn't count. You can't rotate an atom. But you can rotate a diatomic molecule, right? They can spin around an axis, but they can also vibrate. And you can imagine for your polyatomic molecules, the vibrations can be quite complicated, but here you can get them vibrating in and out, towards and away from one another, etc. With the polyatomic, you can only imagine, right? Maybe with a water molecule, you might model it as something like this, little springs attaching the atoms together. That could have some way complex vibrations. Just imagine how it could bounce back and forth. Anyway, these modes, degrees of freedom, get excited in a diatomic or polyatomic molecule, and they absorb some energy, but they don't cause the molecule to bounce around and hit the walls any faster. And so the temperature doesn't increase when you excite these modes. Eventually, these modes will dissipate and cause some translational kinetic energy to increase, but that's a later story. Questions is how can we go ahead and measure, or hopefully theoretically calculate, what would be the specific heat or the heat capacity at constant volume for diatomic and polyatomic molecules. That basically brings us, and here are some of the values that we see. For the diatomics, they become certainly bigger, almost double the specific heats or the heat capacities at constant volume. The polyatomic, 3 or more atoms, you're getting up to even bigger than the diatomics. So certainly the more complex the molecule, the higher the specific heat, the more complex ways it can absorb energy. The answer to this, without getting too crazy, well, is called, the equipartition of energy. Let's do blue. How does energy distribute amongst the degrees of freedom? Thankfully, it's very simple. The answer is equally, but it does depend on temperature. So it's pretty cool. What tells us that? Well, it's this highfalutin advanced, what's called statistical mechanics, which is the application of statistics to a huge system such as a mole of gas. But from statistical mechanics, we get this theorem called the equipartition of energy. And that basically just says, for each molecule, for every molecule or atom of a gas, 1/2 Boltzmann's constant times the absolute temperature energy will be associated with each degree of freedom. Now, really quickly, how does the Kt, how is that going to relate to our original expressions? Well, we'll have to play around with a little bit of algebra, but we'll show you in a second. So just remember this 1/2 kT energy associated with each degree of freedom, though it is temperature dependent. So first we have here's our diatomic gas, and we have our 2 atoms, but it's just showing that you can have 3 components to your velocity. And what that also means, and not to get too highfalutin, but I might as well give it to you straight. Each degree of freedom is associated with a kinetic or potential energy. More specifically, a quadratic potential kinetic or potential energy. Okay, so what we're picturing here is 3 translational degrees of freedom. And what that means is you have a kinetic energy associated, and this is the total mass of the molecule here. I'm really talking about a monatomic gas right now, but diatomic gases have translational kinetic energy and they translate as well. So this is the total mass of your molecule. But you have an X component of your energy, kinetic energy, you have a Y component, and you have a Z component. And this is really what is meant by degrees of freedom. It's degrees, ways of having an energy, a potential or kinetic. Yeah, it's kind of interesting. So for monatomic gases, well, that's all you have. Only 3 translational degrees of freedom. And I'm going to use capital DOF for degrees of freedom to give myself a break, but only 3 degrees of freedom for a monatomic gas. Therefore, each molecule has 3 halves kT energy. Essentially, the energy per molecule is now 3 halves kT because it's 1/2 kT for each degree of freedom. A monatomic gas only has 3 degrees of freedom.